Hello, hello. Yeah.
One last minute and we'll start. Okay, maybe we can get started. We're already delayed. Welcome, everyone. We're very happy to have Supritha Bhowmick with us, who's going to tell us about loops and cosmological correlators.
Yeah. Hi. So thank you all for being here. I am grateful to Professor Supritha Raju for having me here. And today I'll be talking about loop corrections to inflationary correlations, which is based on these two works done with my supervisor, Professor Diptimay Ghosh Farman, who is my senior at arXiv Pune. He'll be joining ICTS soon as a postdoc, and Gordon, who is currently a postdoc at Taiwan. Now, before I start talking about inflationary loops, let me start by talking a little bit about what inflation is. Inflation is an era in the history of the universe, which when the length scales underwent accelerated expansion. This was proposed to offer a solution to some of the observational inconsistencies seen in the standard model of cosmology without inflation. Consider, for example, the horizon problem, which is the apparent puzzle of how are the CMB photons that we're receiving today, how are they so uniform in how are the temperatures of the CMB photons so uniform? Because if you look at two photons that we're receiving, and if these two photons are separated at an angular separation of greater than 4 degrees, that you would see that these photons at the surface of last scattering were outside each other's causal contact. So there's no mechanism which explains why the CMB photons have such uniform temperatures. Inflation offers a solution by proposing that there's a period in the universe when the length scales grew faster than the Hubble horizon, which you can consider as a proxy for region of causal contact, such that in the past, the length scales shrink inside Hubble horizon, and hence causal contact is established. And we're interested in computing correlations of fluctuations on the spatial slice of end of inflation, which is the surface of reheating right here. The reason why we are doing this is because these are the observable output of inflation. And you can map these theoretical predictions to current day cosmological observations, such as the large scale structure or CMB, to probe the inflationary era. Now, to give you an example of what we have measured, consider the simplest candidate of inflation, which is that of a minimally coupled massless scalar field slowly rolling in its potential. The slowness of the roll is captured by this parameter epsilon, which is the slow roll parameter, which is much smaller than 1 during inflation. This slow roll is what gives us the inflationary background. It's not exactly de Sitter, it's approximately de Sitter because the Hubble is not exactly constant. It has a small time varying. And a particularly useful gauge is when we set the inflaton fluctuations to 0, transferring all dynamical degrees of freedom to the metric. Zeta is the scalar, gamma ij is the tensor degree of freedom. Now this zeta, the 2-point function of zeta, you can compute this from the quadratic action, and this will turn out to be this, where h is Hubble, epsilon is the slow roll parameter. The star on h and epsilon denotes the fact that they're not exactly same throughout inflationary era. It has some small time dependence, which is captured, and you set the value of Hubble and epsilon to a pivot. And this time dependence is captured by a very small deviation from scale invariance by this spectral tilt ns. Now this 2-point zeta function can be mapped to, and hence has been measured from the CMB temperature temperature fluctuation, the power spectrum. The amplitude as well as the spectral tilt has been measured. Non-Gaussianities are expected to be small. They have not been measured yet. They are of the order of slow roll parameter. So there are bounds on FNL corresponding to various configurations of the three modes. To be more precise, the quantity that we are computing are in correlations. They're the expectation value of some operator O on some state psi at late times tau goes to 0. This is towards the end of inflation, where the state psi has evolved from some vacuum omega at some early time. Now you can project the free vacuum onto the interacting vacuum omega, do some math and get this in expression. Now to compute this, one can instead follow Feynman rules, where you can compute diagrams like these, where you can have vertices either above or below the tau goes to 0 surface or line, depending on whether these vertices, these interactions are coming from the time ordered or the anti-time ordered part of the NN correlation. And as you can see, these diagrams can have bulk-to-bulk propagators, which are propagators joining 2 points in the bulk. If they're lying on the same side of tau equals 0, you will write down a factor of a bulk-to-bulk propagator, which is given by this Weitman function times Heaviside step functions. But these Weitman functions are what you would write down for a bulk-to-bulk propagator crossing tau equals 0 or a bulk-to-boundary propagator, and they're given by Fk star Fk, where Fk's are mode functions or derivatives acting on them depending on what sort of interactions you have. Finally, you will integrate over bulk points, which are time integrals, and any undetermined momenta you have, which are loop integrals. So as the fields evolve, they'll have some interactions in the bulk, and these interactions, the effect of these interactions will be reflected in the final in correlation that you're computing. And these interactions can be contact interactions, exchanges, or loop corrections. Now, the reason why such loop corrections had not been computed for a long time in literature is because they're very small. These interactions are controlled, the strength of these interactions are controlled by slow roll parameters and factors of Hubble by M Planck. Now, if you look at the 2-point zeta function at 3, this is what it is. If you go to one loop, then by a simple argument of calculating by what scales these are suppressed, you will see that this goes as Hubble 4 by M Planck 4. Now, not only is this slow roll suppressed with respect to the tree level result, it's also suppressed by a factor of Hubble square by M Planck square. Now, how small exactly is this factor? Now, as I just told you, the amplitude has been measured from CMB Planck data. The amplitude goes as 10 power minus 10. Now, you can see that Hubble square by M Planck square must be at least as small as 10 power minus 10, because epsilon is much smaller than 1. So you can see that this loop correction is at least 10 orders of magnitude suppressed with respect to the tree level result. So practically speaking, there's very little hope of ever observing it. Weinberg was the first to stress that even if these loop corrections cannot be observed, one should still compute them to study the theory. And he goes ahead and computes this one loop correction to the 2-point correlation in this work. In this theory, which has n massless spectator scalars, sigma is this spectator field which runs in the loop. And the structure of the correction he gets is this, where C is some scheme-dependent finite constant, and there's a log k by mu. It was pointed out by Senatore and Zaldarriaga that there has to be a mistake in this computation, which is denoted by the structure of this logarithm. Notice that this is a co-moving scale by a physical scale. Now, as one does in loop corrections in flat space as well, one would like to choose a suitable renormalization scale to avoid the problem of large logarithms. To do that here, you have to convert this co-moving scale to a physical scale, and this comes at the cost of introducing a scale factor. But when you do this, you see that the 2-point function becomes dependent on the scale factor, but the scale factor by definition is unobservable. It just corresponds to rescaling of coordinates. So this tells you that this has to be a mistake in the computation. The point was that implementation of dimensional regularization is subtle and de Sitter. And the thing is that since these computations are being done in d dimensions, everything should be in d dimensions, including the modes.
Then the scale factor essentially corresponds to having it's a way of measuring the time, right? So why can't you measure that? Like
the time is measured by the background single field. the background inflaton. The scale factor only tells you by what scales the universe.
No, because you're breaking the time differ by introducing the clock. And so the scale factor in some sense is just like another way of measuring the time, right?
That's not the absolute value of the scale factor at any given time does not mean anything.
That's even that, right?
And I think this correction will persist in the digital digit also when it was not in store. It could also if Feinberg's way is incorrect, then it could also persist in the ATS. And so this would be a statement that you actually are getting answers that depend on log k by some scale factor. It would break the conformal isometry of the boundary. So you don't expect that just loop corrections will break the conformal isometry of the boundary. In fact, in gravity, I think it would be an anomaly, like it would be inconsistent. In theory, maybe it's not inconsistent, but it would be very strange to break the conformal isometry. And the error is actually very simple. It's the fact that when you put a cutoff, you shouldn't put a hard cutoff, you should let it scale with the co-moving image. You can't put the same cutoff at all times. And so if you just make a cutoff scale with where you are with Z, then you'll get the right answer. So that was the...
That's exactly right. As you said, if you compute this diagram in cutoff, you will actually not see this. This computation is in dimensional regularization. If Weinberg had instead chosen to compute this in cutoff, and as he's saying, if you choose if lambda is your physical cutoff, then that would, since the computations, the loop integrals are co-moving scales, the lambda itself, so this co-moving scale will have some time dependence, and that will actually give you, not give you this unphysical logarithm. Since this computation is in d dimensions, if you have to consistently implement dimensional regularization, the entire computation should be done in d dimensions. That's the point. And these are just some expectations that there's something wrong that happened in the calculation. At the end of the day, if you consistently perform a computation, you get what you get. And that's what was done by these people. And they saw that if you actually account for the order delta contributions, that was not done in Weinberg's work, he just used d-dimensional modes. If you account for the order delta contribution, then this unphysical log will cancel. It will turn into a log h by mu. Now this is a sensible result because it's a ratio of two physical scales.
In the Bessel functions, you should use the general dimension.
If you use the Hankel functions, when you use the Hankel function, you use the d-dimensional Hankel functions. Right, that's right.
And Weinberg made a mistake in the sense that he used the 3+1 dimensional.
Yes.
Functions.
Yes. That's absolutely right. So motivated by this, we asked the question of what happens for 3-point functions. In particular, since you have translation invariance, both the legs of the power spectrum are imposed to have the same scale. This is not true for the bispectrum, and you can get richer structure. In particular, you can get logs of ratios of co-moving scales. We were also interested in seeing whether you get such unphysical logarithms for higher point functions as well, and whether they also cancel if you just account for the order delta correction. So what we...
Is there a problem in just doing this cutoff that depends as a function of t?
Sorry?
Is there a problem in just imposing a cutoff that depends correctly on t, on the time? Like that's probably just the easiest way to get the right. Isn't it technically simpler than doing dim reg? The what? Well, this is a scalar field theory, at least, right?
Yeah.
And you just do. I mean, isn't that much simpler? You just impose cutoff that depends on z.
Calculations are actually not simpler in either case, but you're actually correct in pointing out that this subtlety you would not encounter if you were to compute it in cutoff regularization. You're right to point that out.
The reason I asked this is I thought there was something also funny about this Saldariaga Senatore paper, which I don't remember very well, but it was not just that you have to use the d-dimensional delta function, d-dimensional Bessel functions. Even the delta functions had a delta of d plus epsilon. At least in their paper, they seem to write delta of d plus epsilon for the momentum conserving delta functions. And I never understood that. So that's why I never understood the dim reg correctly. Is that correct or that's not correct?
It's true that the momentum conserving delta functions are also d-dimensional, but the point is that these, once you compute the loop integrals, these delta functions have to be d-dimensional because you're sort of accounting for the...
Yeah, but then you can't expand them in any reasonable way. So what do? You just keep them as d-dimensional and in the end put them...
Yeah.
The d-dimensional moment.
But you don't have to, but you never want me to expand. Here there's some subtlety about,
there's some subtlety which Weinberg seemed to have overlooked. So okay, but maybe it in epsilon.
The point is, since you have, you would see that since you have two of these legs, you end up with a loop integral which is of the form of ddp1, ddp2, and then you have a delta function. Now, you can't actually compute this ddp1, ddp2. You have to convert it into dp1, dp2, like convert the phase space integrals to integrals over energies. Modulus of the momentum. And while doing so, it actually comes in handy when you have this delta function, d-dimensional delta function, because you want to get rid of one of these ddp1s or ddp2s. So anyway, we're not expanding this delta function. Right. So we compute the 3-point function using example interactions from EFT of inflation, where we only need till quartic interactions. This is the action of the Goldstone mode corresponding to broken time diffeomorphisms. This is in the decoupling limit where we're ignoring mixing with metric perturbations. And if you want to compute the bispectrum, we would need to compute diagrams like these, where you have either one quartic and one cubic interaction or 3 cubic interaction insertions. Notice these are all at the same order in suppression of the UV cutoff scale. They're all 1 by lambda 6 suppressed. Now, as I just told you the story of how it's important to use d-dimensional modes, now I'll tell you that the internal modes that we will, once we compute these diagrams, the internal modes will be d-dimensional. What I mean by internal modes are the modes corresponding to the fields in the interaction insertions. However, the external modes, which are the modes corresponding to the fields whose correlations are being computed, these are the modes, these are the fields at tau equals to 0, whose correlations are being computed. They'll be taken in d equals to 3. Because once you compute the counterterm contribution, which will cure the divergence of these diagrams, you will see that those counterterm contributions will have the exact same fields and hence the exact same modes, and which they will take away the ordinal delta contributions. So we consider external modes in 3 dimensions, internal modes are in d dimensions in these computations.
Also external lines that get
Yeah. Right.
But that's within the loop, not at the external lines. That's what this is.
Is that what is the case? The bulk to boundary propagator and the testing function self-dimension?
The bulk to boundary propagator, this leg consists of contracting this mode at tau equals 0 and one of the modes of these interactions. So the mode that is at tau equals 0, that's 3-dimensional. We keep it 3-dimensional. The propagator consists of these two modes. And since these are these two modes, or and you can have derivatives acting on the mode coming from the interaction, because these are like pi dot 4 interactions. So this one over here will be 3-dimensional. This one over here will be d-dimensional, because this is an internal mode. As I said, yeah.
But the functions.
I'll come to it. I'll come to the explicit. So as people pointed out that.
Statement is that all the diagrams are same order in this EFT.
Yes, assuming that these are the operators obtained by integrating out the same scale. These are all obtained by integrating out the same.
EFT inflation is supposed to capture anything with the single block.
Yes. Yeah.
That any inflationary theory with the single block.
Yeah.
You use the.
Yeah, that's right.
Time goes slow or something.
Yes.
Why is just a scalar which it becomes a good stone? Time.
That's right. This is the typical. So you write down the EFT of inflation by in this work they constructed in the unitary gauge. You fix time diffeomorphism. You write down all operators that have spatial diffeomorphism invariance, and then you restore time diffeomorphisms by performing this Tuchelberg trick. This pi is essentially this diffeomorphism parameter promoted to a field, and then you consider the decoupling limit. So this is what you're left with till quartic order.
This counting of all these diagrams, we're just doing some dimensional count.
That's right. In canonical normalization, we would see how what is the mass dimension of G3, these coupling. That's right.
Any dimensional coupling is
something by lambda. Yes, absolutely. That's right.
Why is there something like pi?
Something like a.
Shall we derive it?
So these are gold-stone modes. So you have like shift symmetry. Yeah.
Pi is the tile as time if you know those two.
Yeah.
Can only derive it in
But why not a del pi? Oh, yeah, I guess you also have
You can only have del pi squares.
pi not square.
No. Spatial diffeomorphism is still respected.
Yeah, exactly.
Del has a rotation.
Yeah.
In the reciprocal, you hold 1 by lambda to 6 is the decoupling still valid?
Yeah. Decoupling is valid as long as you're working at energy scales that are lesser than the mixing energies. Mixing of this, I can show you. I can come back to this question later. Okay, I'll definitely come back to this question later. I'll actually show you what are the mixing terms and the and these terms and how can you understand the decoupling limit. Like I'll come back to this. Okay, so the point is that since we want to use d-dimensional massless modes, we have to work with complicated Hankel functions with order d by 2. That's the order. Instead of doing that, since these Hankel functions are complicated, we use a neat little trick that was first used in this work by Melville and Peyer, where instead of working with d-dimensional massless modes, they work with d-dimensional massive modes with the mass defined as this. Notice when d goes to 3, m goes to 0. And with this substituted in the order, you will get back nu equals to 3 by 2. So you get back the neat little massless mode functions. This is where the mode function then takes the form. These are just 3D modes, modulo a factor of this. Okay, and you can expand this factor about delta equals 0 to get the structure. And you see that, so the modes then decompose into a 3D part, which is when you consider this factor of 1 in the bracket over here, and an order delta part, which is when you consider this log h tau factor in the first bracket. Similarly, you will also have contributions coming from the measure in the form of a to the power delta. And you can once again expand this about delta equals 0 and you'll get a 3D part, which is just 1, and an order delta part, which is delta log h tau. No, so mass is 0 because we have to work with massless mode functions. But instead of working with d-dimensional massless modes, we want to work with d-dimensional massive modes where the mass is this. I'm just tweaking the mass to take this value. Not me, but
Not even understanding what this got to do. Could have just put b equal to 3 plus the entire universe.
what? Sorry,
I
what?
have not understood what this bought you.
So what this bought me is, if we had not done this, then nu would have been d by 2. So that's 3 delta by 2. So the Hankel function itself is very complicated. It's not simple exponential functions anymore. That's true. That's absolutely true. All I'm saying is, if I define mass to be this, and you plug this in, and then you ask what is the order of the Hankel function, you see that the order of the Hankel function is 3 by 2. That and those are simple exponential functions.
Non-zero d and the non-zero m
Yes.
square.
Non-zero d, non-zero m square, that gives us nu equals 3 by 2, and the Hankel function for order 3 by 2 are simple exponential functions.
Would the following procedure be equivalent if I just solve the Hankel problem in d dimensions and then expand
Hankel problem, what's the Hankel problem?
Hankel as in the Hankel function is some green function for the So
If you
solve
find
that
it-
in d dimensions.
This is the solution of the equation of motion for the scalar in d dimensions. So if you solve the equation of motion of a massive scalar in d dimensions, this is the solution.
Yeah, and then you expand that around b equal to 3 by
It's taken because the rank has a complicated dependence on mass. You just choose the mass to be some clever thing that the rank becomes half integer. And half integer rank Bessel functions are
Spherical.
Still also continuing the mass.
Yes.
But that's the point I'm not understanding. Why are you introducing?
to simplify nu.
Let me.
You want to introduce a mass such that you get spherical.
You get nu equals 3 by 2. Yeah, that's right.
We know that has a smooth limit as you take. So as you said, now you've also given it a small non-zero mass, which it didn't have earlier, and you're saying that what gives rise to.
So I'll just say one thing. In all of the quantities that we are computing, nothing seemed to go wrong. But if you're asking from the representation theoretic point of view, I am not aware of any such studies. that study this, and this would really, yeah, the short answer to that is I don't know.
What worry might be this, that, like usually you do a mass computation and you take mass to 0. You get some infrared diagrams. Now, and already anyway in dim-reg, infrared and ultraviolet are very weak.
In our computations, that doesn't happen because there are enough derivatives all the time.
Yeah.
Yeah.
Okay.
Yeah.
Maybe for the extra
Mm-hmm.
of course. The point is that this will kind of even more mess up the n going to 0 limit and the epsilon going to 0. In the sense that, like, once you, I mean, anyway, you can't see
this expectation, actually, this expectation that's coming from flat space, actually, this is not exactly what happens in inflation. Massless modes are better in some sense. So you don't run into trouble when you take M to 0. There's nothing. I understand that this is coming from like a flat space expectation, but this does not actually happen here.
Yeah. So I think in this also you probably will get into trouble if you're not going to 0, but if your mass. Yeah. But whenever there's. Yeah.
Okay, but maybe yeah. Okay.
Yeah. So the statement, the only thing that you might worry about is that it kind of further mixes up the small mass limit and the dignity. Yeah.
Okay, maybe yeah. Okay.
Oh, why does symmetries are called, right? In this case, once you introduce a mass.
What symmetries?
The shift symmetry and all.
No.
It's gone now. Pi has shift symmetry and the pi plus constant.
You're breaking them.
I mean, doing this is not the same as saying that I'm introducing an m square pi square term in the. I understand your worry. All I'm doing is at the end of the day, I'll take d through 3.
But intermediate state, you're actually breaking that step, right?
Sure.
I mean, it would come from an m square pi square term in that.
Sure.
You use this in d dimension.
Sure.
So that wouldn't cause any problem.
But once again, at the end of the day, I mean, if we are doing it in dim reg, really, we look at the final renormalized answer, where taking d to 3 would not give you any trouble. I mean, that's on.
So that is, yeah, I
Since
but
m goes to.
Normally, if you have an effect, if you are doing an effective field theory of inflation, right? I would have thought that you do effective field theory of inflation in d dimension, then you take d2. That would be a perfectly consistent description, but that's not what you are doing.
That's not what we are doing. We're looking at the 3D EFT.
But maybe when you say mass, the pi is not mass.
Pi is mass.
This is the modes of the pi.
Pi is mass.
This is the mode of the pi.
Yeah, that is a little worrying that you come to shift symmetry.
Yeah, but if you go back, like the start to think even in d dimensions, there are more like pi square.
Yeah, there are not.
So why do we say pi is mass?
I am not saying, okay, let me, to resolve the, I think I should just continue by saying that pi is not massive. There are no mass terms. Clearly, there are no mass terms in the EFT of inflation. If I solve for d-dimensional massless modes, then I have to deal with nu equals d by 2. I'm just employing a trick where I'm saying that I will tweak the value of m to take this value so that when d goes to 3, m goes to 0. Plugging this back will help me get neat little massless mode functions.
But they're already massless, right? This one and that. If m is d,
nu is d by 2. That gives you very complicated Hankel functions. Then the mode functions are not.
But why 3 not 5?
This PF is easy, no, it's exponential by e to the ix, so is that 1 minus ikx.
I mean, the Hankel function is not that bad, right?
You can compute, of course. Senator and Zaldariaga actually compute with. You can do that, sure. Yes.
That function with respect to the you could have already for that. I think one can do it. And what's
We have not tried that, but okay.
This expansion just to the level of mode functions. And we check if this is like what's the additional term that we have added or what drop. Let's say I use the new the terms which had d equal to 3 plus epsilon. Then I would have got some expression by setting m equals
Hmm.
And it would also look like this, that Fk is equal to something into F3D.
Mhm.
Into some expression. What is that term?
That extra term would be proportional to delta.
It would
This
definitely
entire
be
thing
proportional
is,
to delta.
yeah.
That is clear because that's just a series.
Yeah, yeah.
But it might not be log of h tau, it might be something else.
But anyway, since these are one loop integrals, you'll get a 1 by delta, and these corrections are ordered delta square.
You're saying
They'll anyway die down when you take delta.
This kind of expression,
Mm.
maybe I'm saying something wrong. You know, that the true f is equal to f3d into some expression. You could have written down anyway without doing this m squared.
The true fk is not some f3d times yeah, so I can't answer that question because I have not tried that, but I need to.
Data in terms of time, right? Or observe when you do data.
Maybe I should continue, but I'll maybe I should continue because okay. So if
say you get ordered delta square, but in two loops you can get a 1 by delta square.
at two loops, these statements are all about one loop. That's true. At two loops, this might be important. That's true. But since these are all one loop, I'm safe. So these mode functions are, this is what a 3D, this is 3D mode function, and you see that the modes that we now have to work with are 3D mode functions modulo this factor. And this factor we expand about delta equals to 0, as I said, to get a 3D part and order delta part. Same with measure. Right. So then the entire integral decomposes very nicely into a 3D part and an order delta part. The structure of the integral is the following. You have d-dimensional integrals. These are loop integrals. You have some function, some factor of mu. This is when keeping the dimension of the mass dimension of the couplings same in d dimensions as they were in 3 dimensions. You have some time integrals. You have a integrand that depends on loop energies and external energies and time and so on. And then you have this factor. This is precisely what you would get because you're now decomposing the modes in the measure into these nice 3D and order delta parts. And if you're considering contribution from the modes, you include a factor of half. And if you're considering contribution from measure, you include a factor of -1. So Ni is -1 if you're considering scale factor, half if you're considering contribution from internal modes. So we call the 3D part that this integral decomposes into, that is when you're keeping this factor of 1 as d1 and the ordered delta part as d2. Now the structure, to evaluate d1, what we do is we scale this entire integrand by k3. This just makes the computation simpler. If we do that, we see that there's a k3 to the power of delta because these are delta dimensional integrals. N is some integer. And you get, after performing the time and momentum integrals, some function of scaled energies and dimension. Now this may or may not have a divergence. If the diagram has a divergence, you expand about delta equals 0 and you end up with this expression. This is a 1 by delta times some polynomial function of scaled energies and some finite terms as well as some logarithms. These logarithms are of scaled energies. And since there's a 1 by delta here, if you expand this factor of mu and k3 to the power of delta about delta equals 0, you will end up with log mu log k3 times the same function that multiplies 1 by delta and some logs and finite functions of scaled energies, along with other permutations of the diagram. Now notice that the computation for D2, which is when we consider this factor over here in the calculation, is the same computation as that of D1, but now with additional factors of log h tau. And we saw that that effectively computing this D2, which is just the computation of D1 now with extra factor of log h tau, is the same as pulling this log h tau out of the time integrals by substituting tau goes to 1 by kt, where kt is k1 plus k2 plus k3, is the total energy. And you will get some finite non-log functions. So all we have to do once we have D1, all we have to do to compute D2 is just count the number of internal modes, multiply that with half, count the number of vertices, multiply that with -1, add everything, multiply that to D1, and you have D2. And this is order delta. Right, so here is the result of one of the computations where we compute this diagram with a pi.4 and pi.cube interaction. This is the result. Notice you have 1 by delta because this is unrenormalized correlator. You have log of ratio of physical scale, log of ratio of comoving scale, and a log kt. Now with appropriate powers of mu, this log kt would actually be log kt by mu. This is precisely the same unphysical logarithm that was arising in Weinberg's case for the one-loop correction to the power spectrum that got corrected in Senatore's computation by adding the order delta contribution coming from modes and measure. But we see that if we use d-dimensional modes, they still remain. And as these are loop corrections, intuition-wise, we know that we should only trust renormalized answers. And so you can guess what will correct these unphysical logarithms. It's the contribution from counterterms. Now, counterterms will be such contact diagrams, and the operators will be dimension 10 cubic operators, cubic because you're curing the bispectrum, the divergence in bispectrum, and dimension 10 because these were 1 by lambda 6 suppressed. And the general structure will be this, where delta can denote time or spatial derivatives. Because of this, and there's a factor of mu, which we expand about delta equals 0, you get a log mu. Now notice we will apply the same story here. In this diagram, there are 3 internal modes and 1 vertex. So that means 3 by 2 minus 1, which is half, and a log h tau, which can again be pulled out of time integrals by substituting tau goes to 1 by kt. So this is what we end up with. So the contribution from counter term is going to be proportional to this factor over here times some function of k1, k2, k3. Now notice that the relative factor between the divergent 1 by delta and unphysical log, which is a factor of minus half that arises from counter term contribution, is the exact same factor of minus half that also arises between the divergent term and the unphysical log of the bispectrum. So, and since counter terms will take away divergence of the bispectrum, they will have to cancel the unphysical log. So this shows that once you renormalize your answers, the unphysical logs will be cured.
The kinematic structure that appears in the point also.
Yeah, they will be, you can have all sorts of terms here. They will contribute some kinematical factors.
It's the same kinematic.
That's true, that's true. But the important point is that these kinematical factors multiply some factor over here.
Cancel 1 by delta is your.
Yes, yes, yes. That's the crucial point.
The values of 7 order in derivative.
They have to be. I mean, the point is that these are cubic operators, cubic and pi, and these are dimension 10, so they have to be 7th order.
Right, and there was a mention about the same kinematic structure. You get that complicated K3 to K1 to K2 from that counter.
You will have to cure the 1 by delta divergence here. I mean, that's how you will renormalize the divergence of this diagram. We don't explicitly renormalize the theory because we have this argument.
Probably, the structure there is probably constrained by some conformal invariance kind of a default function.
The point is these are inflationary correlators, so it's not exactly de Sitter in the bulk. So you do.
But, yeah, I mean, if you just calculate these 3 the question is, all of us are asking is whether you get that factor, because or else you can't really cancel even the 1 by delta.
Why will you? What stops you from getting this factor? So since we don't renormalize. So since we don't explicitly normalize the bispectrum, I can tell you what happens with the 2-point case, because Senator actually explicitly normalized. There it's easier because your diagrams are 1 by lambda 8 suppressed, so you.
Point structures are very smaller and very basic.
Why is it so hard to do this calculation? I'm not understanding. You did a harder calculation, which is having.
But now, if you want to explicitly renormalize the theory, you have to write down all of the terms. You have to write down all possible terms and then compute their contact contribution, and then you will have to tune the parameters of the counter terms such that you get back the same thing.
Let's not renormalize. Let's just do this diagram. This triple diagram. This three-level contact diagram. What is the kinematic? That should be a simple computation as well. You just have to.
Yeah, you take a That's true. You take a particular structure of the what is this? This counter term, and then you figure out the contact diagram. But the point is that might not solely give you back this structure.
Does it? That's what I mean.
That's what I'm telling you. Since we do not do it for the 3-point function, I can't explicitly show you the processes, the exact counter terms, the fully renormalized Lagrangian. So it happens it's doable, and that happens. It was explicitly shown for the in Senathore's work for the 2-point function.
Yeah, but 2-point function is kinematics and not so momenta.
But you still do have a log k. I agree. There is just a 1 by k cube. That's true. That's correct. That's correct.
Log k actually is not forbidden strictly because you could have had an anomalous dimension for the external length. Maybe that would give you log k. I mean, the real, maybe log k cube, but you could have got log of some other momentum, which could have, maybe, there's some issue of, if the external lengths have an anomalous dimension, that could also have given you, but it probably only give you a log of k1, log of k2, log of k, maybe not a log of k. Maybe right. The other thing I wanted to ask is this: where is the slow roll parameter? Right? This seems to be also an answer in decision. Right? In fact, I'm not seeing any.
Yeah. So this edge dot that you see over here, this is an epsilon h square. Edge dot is epsilon h square. In the de Sitter limit, there's no zeta. In fact, I mean the quadratic of. I mean, in de Sitter, there's no zeta. There's no pi. The quadratic action of zeta is order epsilon.
Yeah, no, I'm just wondering if it's some slight rescaling, you could have written down the same kind of effective action in de Sitter. And I mean, maybe what is happening is you have some, and you would have, I mean, just kinematically, if the structure of the term you could have got also in plain de Sitter. The reason I'm asking this is then you have the strong check of conformant.
Okay. No, the point is that the just as a comment to your question, these interactions possibly break SCTs. You don't have a de Sitter in the bulk. Yeah, SCTs. Yeah.
There's no like Taylor mode in translation with no.
Yeah. So there's no analogous, there's no de Sitter limiter.
Yeah, maybe the tensor, if you did a custom tensor mode.
Yeah, that's not epsilon. Yeah.
That would not have this 1 by epsilon correlation function, and it could have epsilon weight 0. But the scalar correlators have all these 1 by epsilon. No, don't have those. So these are the correlator which you want for scale. That is this. Why would you go to cosmological?
But that might be a question to cosmological.
Yeah, that's good.
Bootstrapping people have a way of. This is a boostless bootstrapping. Huh?
They're computing the same thing in cosmological.
I'm sorry, can you repeat that?
They're computing the same thing. And
you can get the 4-point function by the 3-point function by looking at the 4-point function in de Sitter and taking a particular limit. Right?
1 leg soft or something.
Right,
Yeah.
That keeps the 3-point function slow.
Yeah.
So you can get this to a 4-point function. Can you ask that question? Can you use conformally?
If you take 1 leg soft in the 4-point function, I think you get a off order epsilon. No, maybe I should go back and check. I can't comment.
One of the claims that cosmological bootstrap is useful because you can get the bispectrum by actually doing this, doing the 4-point function calculation de Sitter and then taking a soft limit. Is that correct?
Yeah, I guess you're right. I mean, if you take 1 leg soft. Okay, I have to go back and check, but I think the claim is if you take 1 leg soft in the 4-point, you get the 3-point in slow roll. Yeah, but yeah, sure. I'll have to go back and check the. I don't know. I don't think so. Yeah. No, I don't think so. No.
Just to understand, so we don't have a clear check on the answer here.
On
this answer, because just because this issue of regulation is so subtle, having conformally variant would have been a clear check on whether the answer was right or not. But you're saying in this case we don't have that check. We don't have a good way to check whether the answer
check is that one of the checks is, okay, maybe you can't call it. Yeah. Yes, yes. But if you have to really call it a check, I agree with his comment that explicitly renormalize the theory and show that it actually produces this.
Many others.
Many others.
How do you know they don't? Some of them don't give you like also log k. Maybe one gives you one.
This one actually does give you log k.
Yeah, plus half log k.
I don't understand.
Maybe another counterterm gives you 1 by delta plus half log kt.
The fact that this will give you a minus half log kt comes from this expectation that this log kt is coming from d. Okay, one point is that if you're computing d1 from contact interactions, these are not loop, these are contact, these are tree level interactions, then d1 is not supposed to give you a logarithm. Because these are, if you compute a tree level interaction with 3D modes, you only get a 1 by delta and no logs. Logs will arise when you compute loops. Even with 3D modes, logs will arise when you compute loops. So D1 from 3D modes for tree level will only give you a 1 by delta. It's only when you compute the D2 that you get this log.
This contact diagram at tree level gives you a log. Is that not correct? That's correct.
The contact diagram at in D dimensions.
Indeed.
Right.
Gives you a log.
Right.
Gives you 1 by delta plus log kt.
Yes.
That's because you have 1 by delta sitting outside. So it could have given you a delta log kt, but that's what you're saying. Right?
Yeah.
The question is, you're saying there are other counterterms.
By other, I mean this. If I consider by other, I mean that. By other, I mean you can write down all possible. The counterterms will have this structure. Is all I mean.
That's why you said you didn't renormalize because it was just this one.
No, I said we didn't do this because one can obviously do this, but we didn't do this because we had this argument. But I agree that it's a consistent check to actually show that you write down all possible counterterms, which will have this structure. You compute the contribution coming from them, and you tune it such that 1 by delta divergence is taken away. The argument is that if you can do that, if 1 by delta is cured, which is expected because that's why we're renormalizing this, if 1 by delta is cured, it will definitely have to take away this bracket.
But after take the base, right? Not the log.
No, using the 1 over delta, the counterterms give you 1 plus delta log.
Using the proportional to this.
Yes. Huh?
How do you know that all the jumps with it?
By this argument, by the d1 plus d2 argument. By the d1 plus d2 argument. You count the number of internal modes and vertices, multiply that to d1, and that tells you what this is how you get this factor. Okay, so maybe I didn't.
Bulk-to-boundary propagator was giving you the log. The d-dimensional bulk-to-boundary propagator.
As well as the bulk-to-bulk propagators.
Here there's no bulk. There's only three
Yeah, here's there's no bulk-to-bulk here.
That's where the log case comes from. It's
That's right.
You showed previously. So the bulk-to-boundary propagator has some log effects when you integrated you get this.
That's right.
I have not understood your argument because if there are other counterterms, some other counterterms could have given you 1 by delta plus half log kt. And so maybe how do you know that?
That's not true. That is not true. That is because of this diagram. You see this diagram, there are exactly 3 internal modes and 1 vertex. For every internal mode, you have a half log h tau. For every vertex, you have a minus log h tau. And that gives you exactly plus half log h tau. That's how you know that the contribution is proportional to this factor over here.
So what did you get from the kinematics? The fact that there's one counterterm versus the other, didn't give you tau to any power or anything?
I guess the argument is that all of the counterterms, topologically the diagram just looks like that, and that is always proportional to this factor.
For instance, let's say there was a pi dot, something pi dot to some power.
It does not matter. That would change the kinematic structure that you are getting. No. The point is that no matter what the kinematic structure, so if you consider various counterterms of this, which have this structure, they will all contribute various kinematic forms, but this contribution will always be proportional to this factor over here. Maybe I'm not able to explain. No. Yeah, I'm so sorry. Yeah.
Let's say you had a
Okay.
pi has this log of x tau sitting in it.
Huh?
So the vertex pi dot will differentiate the log of x tau.
Huh?
So it will give you a 1 over tau.
Right. When you differentiate this, so you have an h tau to the power of delta. When you differentiate tau, you pull out an additional delta in front, but you only have a 1 by delta.
Log of x tau. That you showed the expansion previously. The multiple boundary propagator looks like 1 plus delta log of x tau. Good. So
Yeah.
Now let's say differentiate this with respect to tau. And I would get some additional factor. I would get a 1 over tau. So what I'm saying is when you do the d tau integral, it's not that there's only one d tau integral. You might have to do tau log of h tau. You might have to do tau or log of h tau by tau. And those integrals might not always give you log of k total. They might give you maybe, how do you know they can't give you log of k total in some other factor? You see the question? I
see your question, and maybe I'm just.
That's what you. Because the expression looks like e to the I and k tau. That's the momentum expression is giving you an e to the I k total times tau. Correct? Times the log of s tau.
The point is, I can't exactly. I will come back to your question later. I understand the question. The point is, if you take fk dot over here, you have a delta by tau log h tau, but then if you differentiate this, you will get a 1 by h tau. But that does not mess up. The point is, I'll answer your question later. I have to just think about this because right now I'm sort of confused. But I'll come back to this. But the point is that this does not mess up our arguments. I know what you're pointing out, but this does not mess up the argument. I'll come back to this later, definitely. All right. Interestingly, the story with the 2-point function at one loop goes like this, that you actually don't produce an unphysical logarithm if you use the arguments that I just mentioned, because you have a contact diagram with a quadratic operator. So you have 2 internal modes in one vertex, and that gives you exactly 0. So no log kts from the counterterms. And hence you see that you did not actually need to renormalize in order to cancel the unphysical logarithms for the power spectrum at one loop. Because the D2 over here, which comes from counting the internal modes and vertices, there are 3 internal modes and 1 vertex for each of these cases. So that's 3 by 2 minus 1 into 2. That's exactly 1. So the log case cancelled from D1 and D2. And the final unrenormalized regulated correlator does not feature any log case. But for higher point functions at one loop, you would expect to only find no physical logs once you renormalize the correlator. What about 1-point functions?
That does not have any last point.
That was anyway bad because the point is that you will run into 0 modes and so on. That's a separate story altogether. I will not comment anything about that. So the point is that the structure of the bispectrum we found, the renormalized bispectrum at one loop, is you get a log of ratio of comoving scales, log of ratio of physical scales, and a kinematic structure that goes as 1 by k6. So this is still dilatation invariant. Now, as we just saw that there are some subtleties involved in computing this diagram and dimensional regularization, a cross-check is always good. And we see once again that in cutoff, you get exactly the same kinematic factor, which goes as 1 by k6, and the same log ki by kt. And you get a log h by lambda plus some power law divergences. Yes, that's A. Yeah, absolutely. Yes, that's right. Okay, so the model of the story is that loop corrections are small, but they're important. And recently there's a rising interest in studying these loop corrections in various contexts, in the context of production of primordial black holes, understanding high stability of de Sitter, trusting tree-level prediction, robustness of tree-level predictions, and so on. But the next work that I'm going to talk about has more to do with importing aspirations of the S-matrix community into cosmology, namely to understand how do physical properties such as unitarity, locality, causality would manifest as analytic properties of physical observables. In flat space, the key ingredient to achieving this was actually having the knowledge of the analytic properties of scattering amplitudes on the complex plane of kinematics. However, in cosmology, we don't know what is the singularity structure of correlators beyond tree level. There's no systematic understanding. And the reason for this is very simple, because these loop computations are very difficult to compute. Just to give you a flavor, if you compute this diagram with a different quadratic interaction, you will get this result. Now, this is a very ugly result. But if you look past the ugliness, you will see the story that I just told you about. In each of these pieces, the 1 by delta and unphysical logarithm comes with a relative factor of -half, and so renormalization will cure this unphysical logarithm. Now, coming back to the fact that we know we only have a systematic understanding of what happens at tree level. We know that whenever
this log P you're calling unphysical, you see you got a log of K3 by K tau.
That's fine.
That was fine, right?
That's fine. This is ratio of comoving.
Right. And on this dimension computation, it could have given you a log, additional log of K1, a log of K2, and so on. And so the fact that log of K tau is unphysical is
I can't comment on this.
If you did some external like renormalization, bulk-to-bounded propagator, you could have got some additional log of K1, some log of K2. So all I'm saying is it's not always that you can just identify the log K tau and say this is that. Right?
Okay.
It's more subtle than that.
To be very honest, I don't know what exactly these anomalous log Ks are.
It's the fact that I mean, let's just think of Disitter. In Disitter, this field has some dimension 3, but it could have had dimension 3 plus epsilon in the presence of interactions, and that 3 plus epsilon would manifest itself as a log. That log, you're right, would be a log in the external momentum K1 or K2, K3. It would not be a log in K tau.
Okay.
It could combine with a log of K tau, just like this log.
But do we know that it could combine with log of K tau as okay?
If one does the computation including also
Okay.
the external X and so on, we don't know that the particular log of K tau is unphysical.
Okay. Okay. Okay.
You see a log of K tau in space.
Fair. It's just that this is not, once again, this is not a Disitter correlator. Once again, I mean.
I know, but then it's even harder to just say when it is unphysical or when it is.
Maybe in that sense, I think what you're trying to say is that if you write it in terms of log of ratios of comoving momentum, whatever is left log K equivalent, that should be cancelled.
That's right. That's right.
Provided you write it.
Yeah.
Then that everything else, all the logs should be written in terms of
That's right.
comoving.
That's right.
Then whatever is left,
that's bad.
It's a non-comoving object. So that is
Yeah.
So that's the logic that you write it in this way, then the external.
Yeah. That's right. Okay. So far we know what are the exact poles produced whenever at tree level diagrams. So we know that whenever the energy entering a vertex or a subgraph so whenever a vertex or a subgraph becomes energy conserving, you produce a pole at that energy. What I mean by subgraph is a collection of vertices that are either connected by Weitman or Feynman propagators. For example, if you consider a collection of tau1 and tau2, this would constitute a subgraph, whereas tau1 and tau3 would not constitute a subgraph. They're not connected by Weitman or Feynman propagators. Now, since these bulk-to-bulk propagators come with theta functions, you will produce all possible time orderings. Let's just consider one in flat space because computations are simple. Let's just consider the time ordering tau1 greater than tau2 greater than tau3. The modes are simple in flat space. This is some exponential functions. And so this two exchange diagram is just this integral over here. Now, if you compute this diagram, the tau3 will produce a 1 by omega 4 5 plus p2. That's exactly the energy entering tau3 vertex. Then you go on to compute tau2. You can see by adding the arguments of these exponentials that you will produce a 1 by omega 3 4 5 plus p1, which is precisely the energy entering this subgraph. Finally, after computing the tau1 integral from summing the arguments of these three exponentials, you can see you will produce a total energy pool 1 by omega 1, 2, 3, 4, 5. And since there are all other time orderings present as well, you will produce all possible partial energy pools. And since in Disitter, you have the mode functions also have additional factors of tau, you will have other additional factors of tau in the integral, and you will produce higher order pools in Disitter. However, this understanding is missing at this precise understanding is missing at loop level.
I also did the loop thing. So you can also the total energy pool, you can also see it.
Yes, that's true. That's true.
So that is like
Yeah, that is known. Yes. Yes. The poles that you will produce after producing time integrals, if they're independent of the loop momenta, then you can pull them out of the loop integrals and they will survive. But what about the poles that are dependent on the loop integrals, on the loop momenta? You will also produce poles after computing time integrals that are dependent on P1 and P2. No, they'll get affected by they'll be logarithms. I don't know if you can call them.
If you do it in the break, you just get power.
In the loops, you get branch cuts.
In loops, you will get branch cuts.
It's not just pools.
Okay, so sorry, the result was at least that if you look at the leading singularity, that would always K to some power. And so there was, I mean, there's a flat space limit for the leading singularity.
Those results are for tree level. Yeah, you will get a total energy. I agree with this, that you will get a total energy pole as well. Yes, there are the poles, there are branch cuts that you, and you can't, there's no, up until now, there was no understanding of what are the branch cuts and how can you, if you want to understand what sort of singularities come from a diagram, you compute the diagram. There was no other way for us to know. So what we propose over here is we study the integral structure of correlators, and that has allowed us to formulate diagrammatic rules to extract all singularities that will be produced at a one loop diagram with two sides, up to two sides. And I'll tell you what sides are. So using these rules, all you have to do is you have to identify certain subgraphs and the energy entering these subgraphs, and you can immediately write down what the poles and logarithms being produced from this diagram. And I will not go into the details of the integral structure. I'm very happy to discuss this after the talk because these are technical details, but I want to tell you how to use these rules. Before I do that, I want to introduce something called the off-shell correlator. Now, since you don't have time translation, in variance, you don't have a natural quantity called energy that is conserved. Now, it's a matter of definition of what you want to call energy. The very natural definition is you call the modulus of the momentum of each leg as the energy. Instead, you can treat it as an independent variable, and that gives you the off-shell propagator. And an off-shell correlator is just when the internal legs are on-shell. So you relate the energy, you call the energies as related to the modulus of the momentum. But the off-shell, but the external legs are off-shell. And the way you go from this off-shell correlator to the on-shell correlator is just you impose the external legs to be on-shell. The reason why we do this is because there was a study which studied wave function coefficients in flat space, and they have actually classified all singularities to all orders in perturbation theory, and they have used this off-shell wave function coefficient, which is defined in a similar manner, and this has allowed them to classify these singularity structure. Otherwise, what will happen is if you keep working with on-shell propagators, then branch cuts are introduced at tree level only because of the exchanges. So just using this off-shell propagator allows you to classify this properly. All right. Off-shell, there are branch cuts, but the point is that you know that if you treat on-shell, if you consider the on-shell correlator and you look at the exchange, you know this exchange is this K1 plus K2 mod. And if you do that, you'll get root over of K1 square plus K2 square plus 2. So this tells you that immediately at exchange, at tree level itself, you introduce a branch cut. If you use this off-shell definition, then omega 1 and omega 2 are independent of this exchange momentum. And so you don't get a branch cut. It just eases things. That's all I'm saying. Okay. So just to tell you how the rules work, I will use this ugly diagram as an example. This is a 7-point function at one loop. By loop sides, I mean just the vertices of the loop. So tau L and tau R are the loop sides. You have 1, 2, 3, 4 more interactions in this diagram. The first rule is that you will produce partial energy poles. These are also produced from time integrals. This was already expected from. There's a quartic vertex and the others are cubic vertices. So this rule was sort of expected that you produce partial energy pools from time integrals. And if they're independent of loop momenta, you will pull them out of the loop integrals, they remain unaffected. Second rule is, okay, so I'm very unhappy that the colors are not showing up on the slide. I promise you I really colored them brightly, but so this faint blob that you see over here, this is the loop subgraph, which we define as the collection of the loop sites. What we have to do is identify the energy entering the left loop site and the right loop site. So in this diagram, that's P3 plus omega 3, which we call SL. And the energy entering the right loop site is P4. The rule tells you that you will, once you compute this diagram, you will see that there's a log SL plus S and a log SR plus S, where S is the magnitude of the momentum exchange between the loop sites. So that's P1 plus P2 mod. Finally, you have to identify all right subgraphs and left subgraphs, which are defined as the collection of loop sites plus other vertices, with the constraint that at least one of the loop sites should not have exchanges with the other vertices of the subgraph, except of course the other loop site. With this definition, you identify the right subgraph, which lies to the right of the loop, and the left subgraph, which lies to the left of the loop. And you identify all energies in left subgraph that enter into the subgraph except the right loop site. So in this left subgraph, that's omega 1 plus omega 2 plus omega 3. And this diagram has 4 right subgraphs, and in each one of them, you have to identify the energies entering the subgraph except the left loop site. So for example, over here, it's omega 4, 5, 6, 7. For this subgraph right here, which is a collection of tau L, tau R, tau 2, tau 4, that's P5 plus omega 6, omega 7, and so on and so forth.
Subgraphs, can you just think of them in terms of cuts? Like we usually do in standard quantity.
I wouldn't call it cut, but you can look at them as diagrams where these are the external legs and these are the interaction insertions. And
that's what we mean by cut.
okay. No, I'm saying this because cuts there are other cuts in this like cosmological optical theorem. So not cut in that sense, but yeah. So from this, these are so the rule tells you that once you've identified these energies, the logarithms you will produce are at log SL plus S and log SR plus S. And to tell you that this is, once you actually compute this diagram with phi dot cube and phi dot 4 interactions, I won't show you the expressions, they're very long and ugly. I'll just summarize the story. Once you compute the time integrals, you will produce all possible partial energy poles. The ones that involve P1 and P2 are listed here. And once you compute the loop integrals, you will see that you will produce what? Okay, this is not working. Okay, maybe I can use this if this doesn't work. Yeah. I mean the next in the previous one. Yeah, okay, thanks. So once you compute the loop integrals, you will see that each of these partial energy poles turn into a log with the argument, where in the argument E, P1 plus P2 goes to S. And so this turns into a log of S plus S, and you will see that they correspond precisely to the contributions that I just talked about. So the first two correspond to loop subgraph contributions, the middle one, this one corresponds to the left subgraph, and these 4 correspond to the right subgraph contributions. These are precisely the logs that you would also get from following the rules. Okay, so to summarize, so just to tell you that the logarithms that you're producing, the arguments are all obtained by summing the energies over, tells you that if you look at the analytic structure of these correlators now in the complex plane of one of the energy variables, you would see that the poles and branch cuts all lie along the negative real axis. This is because the arguments are all obtained by summing over the energies. This is in agreement to what these people found, where they found 2 all orders in perturbation theory. For flat space wave functions, you also see poles and branch cuts only along the negative real axis of the energy variable.
These results about the wave function here, are they for exact decision?
No, they're flat space. These people study flat space wave functions. Yeah.
Any Storos diagram, singularity in cosmological correlate, maybe I'm missing some things.
Yes.
You're saying that in any Storos diagram, you have the same kinds of singularities, same structures, singularities.
Yes. The singularities always appear from energy conserving conditions, if that's what you're. But this result is only till one loop.
you expected if the background itself has some variation, maybe the lead, you might get other kinds of singularities, no? If the EFToI itself has some kind of background behavior.
What kind of?
Yeah, I'm not saying something very precise. I was saying that in the limit where the background itself has some kind of difference, would you not get some additional kinds of singularities from that background time difference?
These results are for de Sitter quasi de Sitter modes.
Yeah, so that's what I was trying to understand. I thought in the first part you emphasized how your results were some of your results didn't even make sense in the limit where epsilon goes to 0.
Huh?
So, but these results, they're not in the limit just epsilon goes to 0, right? You're saying they're valid for arbitrary FRW backgrounds.
Maybe I'm not able to appreciate this question.
Similarity result valid for arbitrary FRW background.
This one, I can say that these are for de Sitter modes.
Only for de Sitter.
Only for de Sitter modes. Yeah. Yeah. Okay. So just as an example, the 6-point function at one loop, using the rules, you can immediately know what are the poles and branch cuts. And in the complex plane of omega 1, 2, this is out of battery. In the complex plane of omega 1, 2, you would see that there are 3 poles and 2 branch cuts being produced. And in the complex plane of omega 3, there are 5 poles and 3 branch cuts being produced. Right. So now the question arises whether these work for all sorts of interactions, or what sort of interactions do these rules hold for. The point is that when we inspect the general integral structure of correlators, we do this in dimensional regularization. And if we have interactions which give us loop propagators decaying faster than 1 by p for large P, then in the loop integrand we get hypergeometric functions, and we do not know how to handle those integrals. So what sort of interactions do these rules then hold for? They hold for when you have massless scalars running in the loop, you need derivatives. And if you have conformally coupled scalars running in the loop, then polynomial interactions are fine as well. Otherwise, if you have polynomial interactions in massless scalars, you have the propagator decaying faster than 1 by p, and then the loop integrand has hypergeometric functions, and that we don't know how to deal with. However, it's a work in progress that one can still compute these diagrams in cutoff. And we have tried to compute examples where we have complicated interactions that will give you propagators decaying faster than 1 by p and so on. And we see that our rules still hold. We have not found any example where the results deviate from what we expect from the rules. All right, so just so that you believe me, this. No.
Analyze the analytic structure.
Yes. Yes.
But these are 2F1s.
These are 2F1s.
Not high effect.
No, these are 2F1s. Yeah. Yeah. I would love to, if you know how to do it, I would love to talk to you. But we are sort of stuck with this. But yeah, so we don't know how to, we're still struggling with it.
In the flat space limit, the overall flat space pole in total energy, that comes from a very specific point in the integration domain. It comes from in ADS, it comes from the part that's deep in the bulk. Like
yeah.
Is that true of everything you're finding? Or are you saying these poles can come from other domains?
These
poles that you're finding, can they come from other regions in the integration domain, or do they all come from the large tau domain, large tau or small tau, not sure which one, like deep in the bulk? You're doing a momentum space example, so it's not so clear momentum space, but it might be clearer if you wrote it in position space. If you did a partial Fourier transform.
Are you talking about the poles or the logarithms? Because the poles were known from before. The poles that you produce from time integrals, they were known from before. The new thing that we've come up with is what happens at loop level.
I understood what happens at loop level, but at loop level, is it saying that the singularities are all occurring from large tau, from deep in the bulk, or is there no such statement?
The logarithms that you get from these are when you evaluate loop integral over poles that involve the loop legs. Now, I am not sure whether this has some interpretation in this. I can't comment about that, but that's a very nice. Yeah, I don't know.
Singularity, we talk from large people. So I don't think that we have to all go deep in the path. Because if you take, for example, if you do a branch cut, that means that if you take sufficient number of derivatives in block. Now, where will the infinity come from?
If you take,
come from the large integration over.
I'm sorry. If you take branch cuts, then if you take.
The path is not infinite at x equal to 0, but its derivative is infinite. So if you have branch cut, that means if you take sufficient number of derivatives, it will at some point blow up at where the branch cut is, right? So you're looking for some infinite design.
Yeah, the problem is that all of this is in momentum space. I think that's what he's.
So what in the momentum?
Yeah. All of this is in momentum space.
But suppose onward into the position space.
Position space.
The derivative of this with respect to momentum will blow up at the branch point.
And the reason that's simple, actually, the reason it was very helpful in getting these flat space limits was that in that limit, you can say something about the modes and how they behave.
Okay.
You know, in the limit where you have a large Z, the modes can simplify a lot because you're
large Z, large. Oh, yeah.
So that's how those flat space limit results could obtain by saying at large Z, the modes have a simplified behavior. And so it might help you here by if you can recognize that the integration is coming from a particular point in position.
But something like that should be true, right? Because if you have getting some sum of energies, that's where the singularities are. In some sense, that's like some sum of frequency being 0 and some corresponding conjugate time being very long.
Yeah.
I mean, so that's
that time integral is giving the.
Somehow some conjugate time where the subgraph is just.
That is absolutely true. This is exactly what happens when I showed you this two exchange diagram. You have these exponentials. So these exponentials are suppressed minus infinity and they go to 0 if you have enough factors of time.
Also, these laws have some, they extend a little bit more the complex terms of
the point is the singularity structure itself is not known. It was not, there was no systematic understanding of what sort of logs you will produce from loops.
I'd say it might help us. Just expand them out at large tau.
Yeah.
And then look at the structure because then the mode will simplify and maybe that you can argue all this.
Yeah.
So with the x to the n log x, right? If you take sufficient number of derivatives with respect to x, it will blow up at x. Right? And that infinity has to only come from large.
Maybe that might help. Especially since you're in this situation. You know what's happening deep in the dark.
But the point is in all of these computation, the external modes that you're talking about, the ones that are actually taken at tau equals to 0.
All the singularities must be coming from large tau.
The thing is, these diagrams in position space, they often suffer with weird IR singularities. As you know, this 2-point function as well,
No, you don't have to worry about that.
Okay.
I guess maybe do a partial Fourier transform.
Okay.
The translational invariance you probably just get rid of because so that will give you a momentum. And then you look at the remaining integral, but you think of that just a large tau, including perhaps the loop.
Maybe one simple way is just you just have this thing in the momentum space. You just take your energy denominators and do some sugar parameter.
Okay.
Sugar times.
Okay.
Like which is just 1 over x arrays. Like some sugar parameter.
Okay.
We can look at the sugar time parameter times.
No, I don't think I was suggesting something that will simplify the calculation. So it will simplify in particular the analysis of the modes that by looking at them at large tau.
Yeah, but what I'm saying is you can kind of go back to the starting.
Just one question. Why will I look at the modes at large tau? Even the modes that are internal. You mean large tau at deep in the bulk?
That's also large tau.
Yeah.
Large That's negative tau.
But these integrals are, as you know, because of minus epsilon, they are suppressed in the.
No, but that's
Infinity.
that they must be coming from this tau of infinity.
It's not necessary, right? Like you might have like something like 1 by omega 1 plus omega 2. But if it has a pole that put omega 1 and omega 2 poles, but there is a omega 1 minus
Plus omega 2 only has 4 into omega 1 plus.
Or we can pose a positive source.
Maybe we should have
Yeah, sorry. Right, so this is just to show you that this is the result from the explicit computation of this particular diagram. There's a phi dot cube over here and phi dot sigma squares for the other two cubic interactions. Sigma being the conformally coupled scalar running in the loop. This is the result you get. And if you analyze the, if you follow our rules, you will see that this one loop subgraph whose contribution is where the energy entering the left loop site is P3, right loop site is omega 3, and there's one left subgraph and the energy entering this left subgraph is SL1. And you would expect to see log S plus S sort of branch cuts in the answer, and that's exactly what you see over here, here, and here. And notice these are ratios of comoving scales. So once again, fine. This is the renormalized correlator. However, there's one log that I have not yet talked about, which is the log of omega t. Now, in all of the rules that I've told you about, you don't ever produce a log omega t. So where exactly is this log omega t coming from? It's interesting to mention, I will skip these two slides. It's interesting to mention this because of, in the context of a theorem that goes by the name of cosmological Correlator theorem, that tells you that there cannot be a total energy pole for a cosmological linear correlator for massless scalars. However, we showed that this is actually only true in flat space. It's not true in de Sitter because one of the assumptions of this theorem is that from time integrals, you will only produce poles. You will not produce branch cuts. However, in de Sitter, from time integrals, you can produce total branch cuts, total energy branch cuts. So in de Sitter, in regularized cosmological correlators, you will actually produce log omega t not from momentum but from time integrals. And we've also shown that, okay, I'll skip since I don't have time. We've also shown that you cannot produce a partial energy branch cut from time integrals. You will only produce a total energy branch cut from time integrals. And this is not an artifact of Dirac. This will also occur in cutoff. In cutoff, it will appear because of the time dependence in the cutoff. If this cutoff were not time dependent, if you remove this time dependence over here, you will not see log omega t appearing. Finally, no, the cosmological, the tree, there's a flat space tree theorem. They call it a cosmological tree theorem because it's sort of similar to that, where they decompose a propagator into a retarded propagator plus something. Its implications. So this is the work, and this is the theorem that they propose in this work. The tree theorem is just a way to cut loops into trees. No, we're saying the tree theorem is correct. The Kalin theorem is wrong or only applied to flat space.
Is that Kalin theorem coming in this paper?
Yes. They use the tree theorem that they propose in this paper. This theorem is proposed in this paper. They have something called the tree theorem, which is a way of cutting loops into tree. Yes, that's wrong because of the assumption they make that from time integrals, you will only produce poles and not branch cuts. And all of the logs that I've talked about, all of the branch cuts that you will produce, they will never, they will always repackage themselves as ratios of co-moving scales so that the ultimate answer is dilatation invariant. So I will conclude by saying that only trust renormalized answers, otherwise you end up with unphysical logarithms. And now you have diagrammatic rules to extract singularity structure of any one loop diagram up to two sides. All you have to do is identify certain subgraphs and the energies entering these subgraphs. And that you will also, on top of these logarithms that the rules give you, you will also produce a total energy logarithm. The obvious next steps would be to try to generalize this beyond one loop, two sides. What happens if you have a spinning particle or a massive particle in the exchange? what happens for more complicated interactions. For example, if you look at in the spatially flat gauge, if you look at the quartic interactions, these will feature some complicated inverse Laplacian interactions. What happens in that case? Finally, there's a hope of being able to do something along the lines of deriving some form of positivity bounds, which is what these people have tried to do. They have studied the flat space wave function coefficient, and they know to all orders in perturbation theory, you will only have poles and branch cuts along the negative real axis in energy variables if you hold all other variables fixed. And using that and complex analysis, they have shown this relation, which they have verified for some UV models, where the left-hand side is what you compute from the EFT theory. Choosing suitable values of n will pull out various EFT coefficients or linear combinations of them. And on the right-hand side, the psi you see is the UV theory wave function coefficient. There are no known positivity bounds yet because the right-hand side is not positive definite. So the hope would be to see whether one can come up with a clever choice of contour. First of all, whether one can show that the singularities for cosmological correlators only arise along negative real axis. This is the expectation, but this is not proved yet. And whether one can come up with a different choice of energy variable. Finally, to see whether some sort of positivity bounds can be derived. That's all. Thank you.
What is the point about this? Some of those black holes, you have this.
Right. So I'm not an expert, but I can tell you that there was a long debate between, there was a debated paper by Yokoyama and Cristiano, where they showed that if you have, in ultra-slow inflation, if you want to produce significant primordial black holes, then these will affect the CMB scales and the loop corrections are enhanced there. So that severely limits the amount of primordial black hole production you can have. And people argued that this cannot be true because it's zeta is conserved on super horizon scale. But I'm not an expert, but you can check it. So that's the general direction that this interest takes. How do you come up with the rules? We investigated the general structure of the correlators. First of all, we actually computed a few correlators. We saw a pattern emerging, and then we realized that there's something more to the story. So we inspected the general structure of the correlators, and that's where these rules pop out. I can show you actually if you're interested later on how they follow. Yeah.
These log of omega is a log of, these are actually log of mod of KT, right? Can I give you this just a log of mod?
Yeah, when you take the on-shell limit, these are log KTs, yeah.
This is these things you would also get whether they just from the flat space limit. The reason you get it is because you do it in Euler. I mean, the proposal actually was always that it's you should take a look at it. So if you just look at the flat space limit it involves a D, which is a dimension. So you're supposed to do it in Euler. Actually, the claim is if you're working 4 minus epsilon, a particular pole, that pole will become a log when you take D goes to epsilon.
Yeah, yeah.
And
D goes to 3,
so
yeah.
It's not surprising that you get log of omega t. So I'm surprised by someone who takes log of omega t. So just even from D equals you get a log.
But if you don't have 1 by delta sitting in front, then as you take delta to 0, this contribution will. But only if you have loops.
Flat space limit always had a D, was always done in Euler.
Oh no, you're absolutely right. Yeah, that is the surprising part. Yeah, you're right. You're absolutely right. Yeah. Because they missed precisely this part. This is the precise part they missed. That if you, I guess this is what you're talking about. If you have a phi dot n interaction, you compute the endpoint correlator in D dimensions, you will see, so this would be some sort of like a counterterm contribution. You will produce a log omega t. You will produce, that's absolutely true. This they missed, surprisingly. Yeah.
Alien is about inclusive cross section, right? That is from infrared.
It's called KLN because it's sort of reminiscent of the flat space KLN.
Yeah, I agree. But I'm just saying, what is inclusive here and what exactly correct?
Right. So the point is, they say that so if you want to go from wave function to correlator, the map is sort of non-trivial. You have to add up loop level as well as integrals over tree level wave function coefficients, and then you get the correlator at loop. So they said that some log omega t is in loop of wave function and log omega t of tree level wave function will add up to cancel the log omega t of correlator. That's the feeling they were aiming for, but that's clearly that's not true.
It's a theorem about cancellation, not that
Yes.
usually you cannot get log omega, but
No.
some other when you
Yeah.
add things together, they will cancel.
Yeah, and it's wrong.
They agree it's wrong.
Well, yeah. So the point is, Gordon spoke to Melville, and Melville was not happy, but he sort of agreed that, yeah. I mean, we couldn't. I didn't have the opportunity to actually speak to any of the authors directly of this paper. I'd love to one day. Yeah.
One more question to understand. Thank you for being here. Okay, fine, sir. I mean, I do mind the Saturday. If you want many people to come and be with your statistic, then do it. So I thought Friday, but Friday things will stay. So I could just be wrong, but can I one more point comment on this? I don't know, yeah, that I would like to see what is. As you said, there's no way to understand actually do it. Then you would expect this one way data to actually cancel once it occurs. And our argument is just based on the fact that it's expect one way data. Yeah, but it's a bit, yeah, I mean, if you just want the cancellation, it's okay, but I just want to cancel. Yeah. Even the finite terms. So, I just want to see. Let's see, what is Thursday? Thursday, when until midnight? I'm around the. I mean, I don't mind. If you don't mind, I just have to make sure others do. No, but others will not, others might not be. But anyway, why you do that? So then my Monday, then next week. Okay. Monday then, but Monday don't push on this kind of things. When is it? Yeah, I put it on. We'll make up that down. There's an astro something. He asked. What are you talking about? What is that? Something that is a process. Well, that's it. Yeah, so make sure you know that. And I speak to me. Actually, can you add him to the higher? So we need to know about this. Yeah, it's just two questions. You know, please speaking, I'm not so hard. I know. I'm one of the districts. I'm a bit no, but you're unsure what it is. I'm the quantum mechanical side emergency. You're on screen. And the quantum mechanical side emergency. What am I supposed to give a reference about? How does this company I don't understand. okay, is that the ground negotiate that? How do you get a full system by